Hello, everyone. So we've defined the derivative and we computed some particular derivatives using the limit definition. And we've seen that it's a lot of fun to do that, but it also takes a long time. So there are several steps. We have to calculate a limit, maybe do some algebra and so on. So we don't want to do that every time we calculate a derivative. So it would be useful if there were some rules for the standard functions that we see from time to time. And that's where we're going now. So for the next couple of sections, we're going to have some standard derivatives. And then as usual, we're going to have ways of combining those derivatives to get more derivatives. And pretty soon that's going to let us differentiate pretty much anything, or at least most functions that we see. And every now and again, something will come along that's not a standard derivative, and then you have to go back to the limit definition. But for the most part in this calculus course, unless you're specifically asked to use the limit definition, you're going to be able to use these derivative rules that we're going to talk about. Okay, so let's get started. So the first one is the power rule. So it's just a way of differentiating things that look like x to the n, where n is some constant. So it could be x squared, it could be x cubed, it could be x to the half, which is square root of x, and so on. And it tells us that the derivative of x to the n is nx to the n minus 1 for any constant n. So sometimes you see this and you can apply it straight away. For instance, you see x squared, you see, okay, n equals 2. I sub in n equals 2 in my formula. The derivative of x squared is going to become 2x to the 2 minus 1, or just 2x. But then there are sometimes where it's a little bit hidden and you have to recognize the function you have as x to the n for the appropriate n. So for instance, 1 over x doesn't look like it fits the rule straight away, but we remember that 1 over x is just x to the minus 1, right? If you have a negative power, then that flips over and becomes a positive power. So it will be the derivative of x to the minus 1 with x. So here n will be minus 1. So we apply our formula with n equal minus 1. We will get d over dx of x to the minus 1 is minus x to the minus 2. Okay, or we could then rewrite that as minus 1 over x squared. And similarly with square roots, right? So the derivative of the square root of x would be square root of x is x to the 1/2. We can apply our formula with n equals 1/2. So we get a half x to the minus 1/2, and then, okay, if we choose, we can write that back out with a positive exponent as 1 over 2 square root of x. So we just have to recognize what is the n, and if there's a square root, remember we have to do 1 over in the exponent, and if it's a power on the bottom of a fraction, then it would be the corresponding power with a negative sign. For instance, here 1 over x becomes x to the negative 1, square root x becomes x to the 1 over 2. Okay, so now that we managed to compute some more derivatives, let's see one more application, which is finding the normal line. So it's very similar to finding the tangent line, except whereas the tangent line passes through the point and it's parallel to the curve, or has the same slope as the curve, the normal line is perpendicular to the curve. So here is the picture. So we have some curve, we have the tangent line, and basically the normal line is the line that passes through the same point and it's perpendicular to the tangent line. So how do we find this? Remember, if we're finding equations of curves, there are two pieces of information we need. We need a point on the curve, or sorry, a point on the line. Okay, we've got that here, it's at P. And then we need the slope of the line. So how do we find the slope of the tangent? Well, if we know this, sorry, how do we find the slope of the normal? Well, if we know the slope of the tangent line, then we can calculate the slope of the normal line very easily just by doing minus 1 over m. So if the slope of the tangent line at P is m, and let's assume for the moment it's not 0. If it is 0, we'll talk later. So assume that the slope of the tangent line is m, then the slope of the normal line is minus 1 over m. So, if you're ever asked to find the equation of the normal line, well, you know a point on the normal line. You have to find the slope of the normal line. First find the slope of the tangent line, and then do minus 1 over that. Okay, so let's see an example where we're doing this. So find the normal line to the curve y equals x cubed when x equals 1. So we know the point, right? When x equals 1, we find the corresponding y value by plugging into the curve. So y is going to be 1 cubed, which is 1. So the point has coordinates 1, 1. So we know a point on the normal curve, right? It's 1, 1. So we have to find also the slope of the normal curve, and then we can use point slope form to write down the equation of the normal curve. So to find the slope of the normal curve, we first find the slope of the tangent line. So the slope of the tangent line is the derivative. So the derivative of this curve is 3x squared. We evaluate at x equals 1, we get 3. So it's important that we first differentiate, and then afterwards we plug in x equals 1. Right, so I first differentiate with the power rule, n equals 3, I get 3x squared, and then afterwards I plug in x equals 1. If you try to do it the other way, you would get y equals 1. If you differentiate, you would get 0. It doesn't make sense. So when you're finding the slope of the tangent line, differentiate first and then sub in the x value. Okay, so dy dx is 3. That's the slope of the tangent line. And then remember we said that if m is the slope of the tangent, then minus 1 over m is the slope of the normal line. So here the slope of the normal line is going to be minus 1 over 3. Okay, now we have everything we need, right? We know a point on the line, on the normal line. We know the slope of the normal line. We can write out the formula, point slope form, y minus 1 equals minus 1 over 3, x minus 1. Right, y minus y1 equals m, x minus x1. So it's pretty straightforward as long as you remember how to find the slope of the normal line and then remember that you have to use point slope form. Okay, what happens if m equals 0? So here notice that m, the slope of the tangent was 3, which was not 0. What if we have a different example where it's equal to 0? If m equals 0, then that means that the curve is flat or is just horizontal. So if the curve is horizontal, the tangent line would be horizontal. In that case, the normal line would be vertical. So the normal line would be a vertical line of the form x equals a. So for instance, here is a simple example. Let's suppose we consider the line y equals 2. So it's a curve if you like, it's just a horizontal line. So just a very simple curve, y equals 2. And suppose we want to find the normal line at 3, 2. Then it doesn't make sense to do the tangent line and then do minus 1 over m because the slope of the tangent will be 0. I cannot do minus 1 over m. It doesn't quite make sense. So I have to think, okay, what am I doing? Well, y equals 2 is a horizontal line. So the normal line should be a vertical line. So it should be x equals a. And it should pass through x equals 3, 3. Right? So it should pass through 3, 2. So it has to pass through x equals 3. So it's going to be the vertical line x equals 3 in this case. So if the slope of the tangent is 0, the normal is vertical, you have to do something slightly different. Okay, so now we know how to differentiate, every power function, so x to the n. So it would be good to have different ways of combining different functions that we know how to differentiate. So I can, we know how to differentiate x squared and x cubed. Can we differentiate x squared plus x cubed, or can we differentiate 100x cubed? And of course we can, so we have rules for combining derivatives. So let's suppose that c is a constant, and we have two functions that we know are differentiable. So for the moment, we know power rules are power functions are differentiable. Later, we're going to have lots of other functions which we know are differentiable that we can apply this to. So we start with these building blocks, and then we can put them together. So the derivative of a constant times a function is the constant times the derivative. So if I know how to differentiate f, I can also differentiate 10f or 100f. It's just going to be 10 times the derivative of f or 100 times the derivative of f. Another way to think about it is you can just bring out the multiplicative constant. And the same with similarity with sums, right? If I know how to differentiate each term, the derivative of the sum is the sum of the derivatives. So instead of differentiating f plus g, I can just differentiate them separately and then add them together. So using this, we can differentiate any polynomial. Why? Because polynomials are things that look like, say, I don't know, 5x cubed minus 7x squared plus x plus 1, right? They're a combination of things that look like powers of x and constant multiples and adding or subtracting things. So we can handle any one of these with these rules. So for instance, here is a polynomial, right? X to the 2020 plus 2x to the 5 plus pi. Okay, the sum rule we have says if we want to differentiate the sum, we can differentiate each piece separately. So if we differentiate the x to the 2020, we use the power rule with n equals 2020. We get nx to the n minus 1 or 20x to the 2019. Next up, we have 2x to the 5. Okay, the derivative of 2x to the 5 was, remember by the constant multiple rule, it was twice the derivative of x to the 5, right? Instead of differentiating 2x to the 5, I can just differentiate x to the 5 and multiply by 2. So differentiating x to the 5 will give me 5x to the 4. Then I have to multiply by 2, I will get 10x to the 4. And then lastly, I have pi. Okay, pi is just a number, so don't let this confuse you. It's just a constant. So as you can check with the limit definition, for instance, the derivative of any constant is 0, or it makes sense with the graph, or if you really want to go back to the power rule, you can use the power rule with n equals 0. So derivative of a constant is 0, so that's all the terms. And any other polynomial, you can follow the same strategy. Okay, I don't want to say too much in this class why everything works. If you really want to know why things work and you want to go into the details and really understand things very carefully, then I recommend doing advanced calculus, which is a really fun and interesting subject, or maybe delving into real analysis. But for the moment, let me give an example of like an instance of how we prove these kind of things. So why is the derivative of the sum of the derivatives? So let's suppose that f and g are differentiable, and then we consider the sum, which I'm going to call s for sum. And that's a new function, and I want to figure out how to differentiate it. So if I want to differentiate something that I've never seen before, what can I do? Well, my only option is to use the limit definition. Right? Remember the derivative of a function, I had to do, in this case, s of x plus h minus s of x divided by h, then I had to take the limit as h goes to 0. So the only thing I can do is start off by looking at this difference question, s of x plus h minus s of x divided by h. That's my definition, right, of derivative of s. And then I want to write out, as we've done in all the examples we've seen where we computed derivatives using the limit definition, I want to write out what this actually means for my function s. So s is f plus g. So whenever I had s of x plus h, I can evaluate that by replacing x by x plus h. I get f of x plus h plus g of x plus h. And then similarly, if I want to take away s of x, that means taking away f of x plus g of x. So I get minus f of x minus g of x. So I get this big mess on the top. And then I remember what the goal is. We want to be able to differentiate the sum in terms of the original functions. So I want to split off everything that came with f and then split off everything that belonged to g separately. And you can check these are really equal. So all we did was some algebra. And then if we try to take a limit, well, we recognize this first term is, it's the limit that appears in the definition of f prime. And this is the limit that appears in the definition of g prime. So the first term is going to go to f prime. The second term is going to go to g prime. So in the limit, we get f prime plus g prime. Okay, but what did I do? Well, that is also, if I look on the left, if I take the limit of whatever is on the left, that's the definition of s prime. Right, so we've managed to show that the derivative of s is f prime plus g prime. So as we stated, so that was the sum rule. You could do a similar thing with constant rules. It's just with the constant multiple rule, it's just as easy. But with products and quotients and compositions, it's more tricky. Let me say, with products and quotients, it's possible to do it with algebra, but you have to be a little bit more careful with the algebra, and the formula that you get is not as simple. So the derivative of a product is definitely not the product of derivatives. There's a more involved rule that we're going to talk about. But essentially, you can get it just from doing this kind of algebra, playing around, and then taking the limits. But probably we'll pass up that. Okay, so that's it for today. So we talked about the power rule, how to differentiate things like x squared, x cubed, square root of x, 1 over x, and so on, and how to put them together with the sum rule, constant multiple rule, and also how to find the equation of the normal line. Thank you. See you next time.